What I'd like to do is first simplify the problem by, instead of having the 2 points at different levels, let's have them at the same level. And say we'd like to get from this point to this point. And in this case, it's obvious that the straight line isn't going to do anything because the ball is just going to sit there. But if you construct a curve, let it be, for starters, a fairly shallow curve. Because the nice thing about a shallow curve is, what is it? Is it a parabola? Is it a circle? Or is it any kind of function? Well, it doesn't really matter, because when you take a curve that's shallow enough, they're all the same. Basically, the term that dominates is the quadratic term in the function. And it might as well be a parabola, or it might as well be a circle. Now, if it was a circle, you could imagine, instead of having a roller coaster carrying the ball, you could trace back to the center of the circle and hang the ball from a string. And in this case, it's exactly a pendulum. We can forget about the roller coaster altogether and just imagine the ball hanging from a string. You're looking at motion constraints to follow a certain pathway, and what the ball is going to do is the same, whether it's inside a bowl or hanging from a string. Now, the funny thing about this example is you can see, supposing it took 1 second to get from point A to point B. Well, you'd say, is that the fastest you could have got there? What we know about pendulums is that this 1 second, that if it took to get from here to here, it would also have took the same 1 second if you started over here and only went this far. And conversely, if you pulled it back a little bit farther, so that you started over here, and then you could get all the way up to here, it would still take pretty near 1 second, because the time of a pendulum isn't all that dependent on the arc, the length of the swing. It'd still take pretty near 1 second. And if you believe that this is true of pendulums, then clearly the farthest distance you could cover in 1 second using a circular arc would be to pull your arm all the way back to a vertical, and then you could go from here all the way up to there in 1 second. That would be the farthest you could cover with a pendulum. And it's interesting that about 100 years before the problem was solved by Bernoulli, Leibniz, L'Hopital in France, and of course Newton in England, Galileo guessed that the solution of this problem should be that the trajectory is a circle. And Galileo is damn near right, but fails to be right in the same way that the time of a pendulum fails to be constant, because you know it is only an approximation that the pendulum traces the same time period as the arc is bigger or smaller. As you pull it back to make a more drastic swing, it fails to be true that the swing of a pendulum occupies the same time period. And if you try to fix up a pendulum so that it would have truly a constant time period, the first thing you do is get rid of the string and do it in a roller coaster so that you could shape the roller coaster any way you want. And when you started your roller coaster out on the bottom, you just keep it the same as it was because it works fine. But you find as you get near the ends, you would have to follow a different trajectory near the end points. And it's not all that hard to write a formula to describe the conditions that this curve has to describe locally, which is to say in the form of a differential equation. And once this curve is constructed, it turns out to be a curve which Bernoulli described in his preamble to the problem. He said, "You will be amazed and delighted when you solve the problem to learn that it is a curve well known to geometers. In fact, a curve called a cycloid."